Hey coders, this better. Hey coders, hope you're staying safe at home in these COVID-19 times. These are really difficult times for everybody, but we should always look on the bright side. What would be a better time to learn something new, improve yourself, and practice for your future coding interviews? Personally, I decided to check my skills and participate in 30-day lit coding challenge, which I'm encouraging you to check out. Connect with me on LinkedIn and check out my daily comments about everyday problems and check out the link to the challenge itself down in the description. I'm gonna choose the most interesting questions from the challenge once it's over and do a review on those. But today we're going to be looking at a really interesting question called Wiggle Sort, which appears to be asked at such companies as Google, Airbnb, Facebook, and Microsoft. And there are actually two different versions of this problem, and the second one, the less frequently asked one, gave me a lot of troubles, and I thought that's going to be really interesting to share it with you guys. So let's go. So we're looking at Wiggle Sort, medium question. Given an unsorted array nums, reorder it in place such that nums0 is less than equal nums1, and nums1 is greater than equal nums2, nums2 less than equals num3, and so on. Let's look at the example. It's pretty straightforward. We have 3, 5, which is 3 is less than 5, 5 is more than 2, 2 should be less than 1, it's not. 1, 6, 4. One possible answer, 3, 5, 1, 6, 2, 4. Okay, we'll get the question. Let's jump into the actual algorithm that's going to help us to solve this question. So we're looking at our problem. The first thing you always need to do is to understand the problem completely and analyze it. So let's look more into the problem. What's the first thing you notice? The important thing you should notice is that one of the constraints is less than equal and greater than equal, which means it's not a strict less than or greater than. We can have equals. That's going to be important in our algorithm. We start analyzing our example and what can actually help us to get the constraints right. The first thing you should think about is it's always easier to work with sorted arrays, so we can sort it, right? We sort it and then we check the constraints. One is, since it's sorted, is going to be always less than 2. Now we're going to go to 2 and 3. Let's have two pointers, 2 and 3. We compare them. 2 is obviously less than 3, and our constraint is that it should be greater than equal. So we can swap these numbers. 3 and 2. Okay, our constraint is satisfied right now. What are we doing next? We switch our pointers and add 2 to their positions. Okay, we have one pointer pointing to 4, other pointer pointing to 4. So what constraint should it be right now? We have 1 less than 3, 3 more than 2, 2 less than 4. Obviously, because as we sorted, we make sure that this number is less than 4. Okay, then 4 should be greater than or equal to other 4. 4 is equal to 4. We can go next. Switch pointers. Then we have pointers pointing to 5 and 6. 5 is greater than 4, as we discussed, because it's sorted, but 6 is greater than 5, which our constraint should be otherwise. Then we swap. 6, and 5. So it's 1, 3, 2, 4, 4, 6, and then 5. Our problem is solved. Let's look into the complexity. What's the complexity? Time complexity is going to be O big O of n log n, because sorting part takes n log n time if we use the most optimal sorting algorithms. It's quicksort, merge sort, or something. And then we do one path through the array and swap the numbers, which is n log n plus n, which would discard n because we're using asymptotic complexity. Space complexity is going to be big O of constant, big O of 1, because we're not actually storing any of the elements, not copying the array or anything else. But is it the most optimal solution we can get? We can actually do better. What's the better way? So we have this array 3, 5, 4, 2, 1, 6, and 4. And if we notice, our constraints are tightly connected with the indexing and the position, meaning even indexes should be less than odd indexes, which is 3, 5, 2 is actually index 0, index 1, index 2. 2 should be less than index 3, which is the odd index. These numbers should be swapped. This approach can actually help us to do it all in just one path. So we also have two pointers, which is 3 and 5. And we start checking our condition. And whenever our condition is not met, we just swap the numbers. Here, the, let's say, even index is less than odd index, 0 index, index 1, 3, and 5. It actually satisfies our constraint. We'll go further. Here, even index is less than odd index, satisfies our constraint. Here, even index is actually not less than odd index, so we should swap. But the important thing to notice here is if we swap these numbers, 4 and 2, the condition of 5 being bigger than the next number, than the even index number, is still met, just because 4 was less than 5, and if 4 is bigger than the next index is also going to be less than 5. So our constraint still satisfied. We'll go further, still satisfied, 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 and our problem is solved. So you can probably already guess the complexity. Complexity is just going to be O of n. We just do one path through the array. And the space complexity is also going to be constant, because similarly to our first approach, we don't store anything. So let's jump into the actual coding. Here we go. So let's implement our first approach first. As we said, we need to sort the numbers, which is sort the array nums.sort. Then we iterate through the array in range from 1, because we met the first number, because if it's sorted, 1 is already going to be less than, for example, 2. Then length of our array -1, because we don't want to go out of range. And then we just swap the numbers. Nums I and nums I plus 1 equals to nums I plus 1 nums I. The reason we put in negative -1 here is because when we're iterating, we're using index I plus 1, so we're just making sure that we're not going out of range. 2 here means that we incrementing our I by 2. Let's run it. Accepted. Submit. Our submission is accepted. Okay, that was fine. But this solution is, the complexity for this solution was n log n, and we're trying to solve it in n complexity. So let's do that. As we talked, we can do it in one path, which is for I in range lengths of nums minus 1. What do we do? We check if it's an odd or even index. I mod 2 equals 0, meaning that it's even index. And in even index, for example, here 3 should be less than 5, but if it's bigger than the odd index, we would need to swap. Or next constraint is if index is, my bad, mistype it here. If index is even and nums I is less than nums I plus 1, which means that odd index 5, it should be bigger than any even index. 5 should be bigger than 1, and if it's not, if it's less than 1, we need to swap. And we're not including the cases when it's equal because it satisfies our constraint. So nums I and nums I plus 1 equals to nums I plus 1 and nums I. Let's run it. And it is accepted. Let's submit it. And our submission is accepted. This would be the most optimal way to solve this problem. But as I promised, we're going to look at 2 versions of this problem, and the next one is going to be Wigglesworth 2. Let's look at this problem. So given an unsorted array nums, reorder it such that nums 0 strictly less than nums 1, and nums 1 is strictly more than nums 2, and so on. We have a couple examples, 151164, and one of the possible answers is 141516. Next one, 132231. Possible answer is 231312. We can assume that all of the inputs has valid answer. And there's a follow-up question if we can do it in big of n time and or in place with no extra memory. So let's try doing that and jump into the algorithmic part. So here's our problem. As we discussed before, we have the strict less than sign and greater than sign. So what would be our first approach? We can obviously do as we did in our previous challenge. We can sort the array. Sorting the array, and what we can see from this array. One of the possible ways would be to split the array into 2 halves, which would give us the half array with the smaller numbers and the half array with the bigger numbers. So intuitively, we can put the smaller numbers into even indexes and bigger numbers into odd indexes. So it looks like it would work, but what's the problem with it? Seems like it's working. 1 is less than 2, 1 is less than 2, but here it's 2 should be bigger than 2,
but it's equal. This doesn't clearly work. So, what would be the solution for this? One of the possible solutions would be to reverse our half arrays. So, this way we're putting the colliding elements, which is 2 and 2, as far from each other as possible. Merging the array, we get 2, 3, 2, 3, 1, 2, 1, 2, which satisfies the constraint. But remembering our follow-up question, which asks us to solve the problem in linear time and constant space complexity, we clearly didn't do this. We sorted our array, which takes n log n time, then we split it into halves and reversed it, which we would need to keep the reversed array somewhere, which also takes linear space, and then we merge them together. So how do we do this in linear time and constant extra space? So there are two things that we need to think about. The first one, our first step, would be splitting the array into half. So how do we split array into half? Or do we actually need to do this? Indeed, we just need the middle element, median, which we can get using quick select. Quick select is a really popular algorithm, and if you're not familiar with it, I'm gonna attach the link down below, and you should definitely read on it. It gives us average time complexity of big of n and space of constant, which is pretty good. The time complexity is not guaranteed, but the other algorithm that can give us the guaranteed time complexity of n would also take the linear space complexity, which is just a trade-off that you need to talk about and let your interviewer know that you understand this and you just decided to go with quick select. We're gonna go with quick select right now because it's actually easier to implement. Second step is putting smaller half into even indexes and greater half into odd indexes. So how do we do this? In my opinion, this is the most tricky part, and we can think of this problem as of Dutch national flag problem with modified indexing. So we're using quick select to get our median, and quick select also sorted our array. Nice. And how do we go about indexing? So here's the formula that we can use for indexing, which is I gonna be our original index. We're gonna map it and multiply by 2 plus 1. This is just gonna make sure that we're iterating over even or odd indexes. And what are we doing here? Here n is the length of our array, and this is bitwise OR operator, bitwise OR 1. So actually what it's gonna do is gonna map the length of our array, which is for example 8 right now. Bitwise OR 1 is gonna give us 9. We're just making sure that this number is gonna be odd for us to be able to map our indexes. If they go out of range, we map them back. If we started with odd indexes, they're gonna map back to the beginning to even indexes, which is gonna help us in future. And if it's a little bit confusing right now, you're gonna see it more clearly when we're gonna go through the algorithm. And modulus just helps us map back. So we have our array. This is the representation of Dutch national flag problem. Here's our indexes. I is gonna help us to keep track of odd indexes that we start with. J is gonna help us, in this case, to keep track of our even indexes. And K is just gonna make sure that we iterate over all of the even and odd indexes. So we start with indexed k equal to 1. What we want to do is we want to go to this index 0, 1, 1. This element is less than median. So we want to put it to the end, to our even index, which is indexed j equals 6. So we go 0, 1, 2, 3, 4, 5, 6. And we check our 6, we swap the elements. So right now we have our element 1, which is one of the smaller elements. We have it in even position, which is exactly what we want. We decrement j, indexed j would be 4 right now, which would be this position. We would go to check next if we see an element that's less than our median. Right now we didn't change k, so we go back to 3 and check if 3 is less than or greater than our median. Clearly it's greater than, so we go to indexed I, which keeps track of our odd indexes, and we would want to swap elements in indexes indexed k and indexed I. But these are both 1, so we don't do anything, we just increment I and k. We go back to check k now. So k is 3. We go to index 3, 0, 1, 2, 3, which is 2. We compare 2 with our median, which is also 2. They're the same, so we're not doing anything. We're just incrementing k. So index k would be 5 right now. So 0, 1, 2, 3, 4, 5. It's also 2, also equal to median. We just increment k one more time. Go back, check indexed k would be 7. So 0, 1, 2, 3, 4, 5, 6, 7. We see 3 here. 3 is greater than 2. So this means that we need to put 3 into our odd index. We go to I, indexed I equals 3. We go 0, 1, 2, 3. We have this 2 here. So we swap 3 and 2 and increment our I and k. So we have index I5, index k equals 0. We map. So basically we went through all of the odd indexes right here right now, and all of those odd indexes have the elements from our so-called array with the bigger numbers. So it's 3, 3, 2, and 2. Now we need to check all of our even indexes and make sure that those also contain our smaller numbers. So index k equals 0, we check 1. 1 is less than median, so we go to indexed j, which is 4, 0, 1, 2, 3, 4, and we swap these. We swap this 2 and this 1. So we didn't change k, we swapped it, we have all of our constraints satisfied, and we go to check index k again. Index k equals to 2, 2 equals to median, we just increment k. At this point k and j are the same, which means we checked all of the odd indexes and all of the even indexes, which j checks even indexes, k checked all of our odd indexes and mapped back to check the beginning of our even indexes, and we terminate the loop. And right now indeed we have the solution, which is 2, 3, 2, 3, 1, 2, 1, 2, which satisfies all of our constraints. So the time and space complexity are going to be, average time complexity is big O of n, and space complexity is just constant. You should definitely talk through this with your interviewer and let him know that you could have done guaranteed time complexity of big O of n, but the space complexity would also be big O of n, and talk with him about all of the trade-offs. So we have the working algorithm now, and here's the time to implement it. So let's see our implementation. The first thing we want to do is we want to implement quick select, which we're going to pass our array and the number that we need to get. We need start equals 0 and equal length of nums minus 1. I'm going to be doing this while true. And what we're going to be doing, we're going to be getting the pivot. Well, I already imported random. Random dot rand end start to end, and then we're gonna have I, J, and K, where we have start and start, and while k less than equal to j, we're going to check nums, so we get the pivot right away. Want to check if nums is less than pivot. If it is, we're gonna nums I and nums k, gonna swap the elements. And increment both, and then if nums k bigger than pivot, gonna num k and nums j, gonna swap those. And gonna decrement j and else, which is gonna increment k. This looks about right. Then we're gonna check if our element is in the right position. If it is, we're gonna return pivot. If it's not, if n minus k, and if n minus 1 less than I, we are just gonna choose I minus 1 as end, and if it's bigger, we're gonna choose I plus 1 as start. And this looks about right. If we have any bugs, we're just gonna figure it out later. Median would be quick select. We're passing nums and we're getting lengths of nums plus 1 divided by 2. We got the median. Now we get I, j, and k that we're gonna use to swap elements. And here we're doing the similar approach we did for quick select. We're using k less than equal to j. If as we talked about, we need to define index that are gonna remap our index to modified index, which is gonna be 1 plus 2 multiplied by I modulus length length of our nums bitwise or 1. So we wanna check nums, our modified index k, if it's bigger than median. If it is, we want to put it in the modified index I. Index I, and we're swapping with the modified index k, and we increment both. And else we're doing elif nums modified index k if it's less than median. What we're doing nums index k, and we're swapping with nums modified index of j, which is gonna map to our even indexes at the beginning, and nums index j, nums index k, and we decrement j, and else we just increment k. Looks about right. Let's run it. Time limit exceeded. I think I'm incrementing everything here. Let me check. Okay guys, so it was a typo right here. I just typed k plus 1, should be k plus equal 1. And some more typos. Let's run it again. Should be nums. Finally it worked. Let's try submitting it. And yay, our solution works. So let's go through the solution step by step. Here we're just implementing quick select. I'll give it as a homework. You can figure it out how to implement quick select. It's not the interesting part. Here we're getting the median. Quick select, we're just getting the middle number. Index, we're redefining our indexing, remapping the indexing according to the formula I showed you in the presentation. I is the current index multiplying by 2 plus 1, length of nums bitwise or 1, which is just getting us the nearest odd number. Here we're defining I 0, j last element in the array, k 0. And here we're swapping the numbers. If nums redefine k, which we start with the odd number, is bigger than median, we swap it with I, which we keep track of to keep track of odd indexes. We swap and put it in odd index, increment both. If it's less than median, we go to j, which we keep track of j to keep track of even indexes, and put it to even index. And if it's none, we just increment k plus 1. So yeah guys, that's it. I think that this question is much more complicated than it appears to be at first. And even though it's marked as a medium one on LeetCode, I really think that this one should be a hard one because it involves a lot of different algorithms, and you need to be familiar with quick select and the Dutch national flag problem, and have a really good intuition of how to come up with the indexing. So I hope you enjoyed this video. Please subscribe to the channel and press the like button on this video. Watch the other videos. I encourage you to participate in 30 days LeetCoding challenge. If you need any help, don't hesitate to reach out to me. I'm always open to helping people. I'm gonna put this code in on my GitHub account and give a link to it if you want to check it out. And yeah, guys, keep coding and see you later.